Okay, today we're looking at some of the stuff that scares students the most, and it really shouldn't because it's not all that bad. We're looking at voltaic cells. Voltaic cells are spontaneous, also known as galvanic cells, also known as batteries. In the world of electrochem, you basically have these categories. Electrochemical cells is the big heading, and then that's split into two parts, your spontaneous and your non-spontaneous cells. Today we're looking at the spontaneous cells where we're going to have a positive voltage, and these are your voltaic cells, again also known as galvanic. And then later on Friday actually we're going to be studying the electrolytic cell, or your non-spontaneous cell. Look like my writing is crazy. Okay, so you guys are going to be responsible for identifying all sorts of things in the cells. Are you going to have to outright draw one on the AP? Probably not. You will sometimes be responsible for labeling, showing arrows of how the electrons are flowing, showing movement of ions. That all shows up. But we're just going to draw them from scratch, because if you can draw them, then you can label. We're going to start. This particular redox reaction is the reaction that's running this cell. It is the movement of electrons from oxidation to reduction that's harnessing that energy. So we always start in two separate vats. Okay? Each vat represents a half reaction. It's a half cell. So oxidation will be in one of the cells. Reduction will be in the other cell. And then the electrons will flow from high potential to low potential from, which way do they flow from? What's losing electrons and what's gaining? Oxidation is losing and reduction is gaining. So it's going to flow from the oxidation half cell to the reduction half cell. So you can decide, I'm not going to dictate what goes on the left and right. I don't like when people make students put things left and right. You need to be able to handle these under all circumstances. If I turn this thing upside down, you should then stand on your head and be able to do it. Okay? So where do you want to start with? Cobalt half reaction or the copper on the left? I don't care. Cobalt. Okay? So we're going from cobalt to cobalt +2, and then I want you to balance that little half reaction. Until you become rock stars at this, I want you to put your half reactions underneath the half cells. And then we have our other reaction underneath it. We're going to do copper +2 electrons goes to copper. Now the components of the cell are going to be some sort of solution. And at standard conditions, what's the concentration of that solution? 1 molar. And it's got an electrode in it. Okay? And then another electrode in the other one. Now, what those are made of are the parts of your half reaction. So this is actually going to be cobalt solid, that electrode is going to be. And then your solution is going to be 1 molar cobalt +2. And it's probably cobalt nitrate or cobalt chloride or something else. But we don't care about the anion. We just care about the cation, because that's where our reduction or oxidation occurs, depending upon which half reaction. So what is this metal going to be? That's a copper electrode. And what's in here? 1 molar copper 2. This is a pretty pink. You remember, cobalt +2 is like a pinky red. What color is copper 2? If you don't know this, I might have to come over and physically hit you. Thank you, blue. I just threatened my students on video. That's awesome. I'm going to get fired. It's going to go to the school board. You know I really wouldn't hit you, right? All right. So now, in order to harness the electrons, we need some sort of wire here that connects them. Your wire does not have to be loopy. I like loopy. People call me loopy. And let's go ahead and talk about these electrodes. These electrodes have names based on whether oxidation or reduction is occurring at them. So looking at cobalt going from 0 to 2, is that oxidation or reduction? That's oxidation. And then what's this? This is reduction. And it's doing that thing again. It's this time of day, guys. Okay. The name of the electrode, does anyone remember from last year? Anode and cathode, which is which? Oxidation occurs at the anode, and I'll tell you how to remember it in a second. Reduction occurs at the cathode. There are a couple ways you can do this. The most common way that I've heard is saying red cat and ox. Reduction occurs at the cathode. The anode has oxidation occurring at it. Another way you can look at it is you can say vowels go together and consonants go together. All right, let's talk about those electrons. Remember, oil rig, oxidation is losing, reduction is gaining. Electrons flow from what to what? No, we're not doing signs here. Positive and negative, we haven't even indicated yet, okay? Electrons flow, and that's what physics has done to you. I smite you, physics. Anode to cathode. Because they're going, and just look at these half reactions. See how that's losing and that's gaining? Okay, so if you get lost, having those half reactions there help because you can see exactly what's going on. So the electrons are going to flow from anode to cathode. The little trick I have for that is that electrons flow alphabetically. What's alphabetical? O to R and A to C. Okay? All right. So when the electrons flow, we end up getting a buildup of charge here in this right cell because electrons are going in there, correct? So what's the buildup of charge on this side then? Positive. Once one electron goes to the cathode, why would any more want to go? Right now, they wouldn't. This cell would go like boom and be done, finished, because there would be a charge buildup going on. So we're actually missing a pretty crucial part of this cell. Does anybody remember what it was called? A salt bridge. A salt bridge, back in the old day, now batteries look so different, and you're going to actually use filter paper when you make your little half cells in your well plates. But it used to literally be a glass tube, a U-tube, and it would have a plug, not YouTube, oh Lord, a plug of cotton in the end. Yeah, because I see the connection between that and YouTube. And in it is a solution that would help neutralize the charge buildup. We want to pick a solution that's not going to cause interference with anything else. So we want to pick something with ions that are always soluble. What kind of ions are always soluble? Nitrates and the alkali metals. So group 1 nitrate is our best bet. What group 1 nitrate do y'all want to put in here? NaNO3. All right. Okay. So you do, and this showed up 2 years ago on the AP. I graded this question. They asked for direction that the ions flowed from the salt bridge. So we said that electrons are going this direction. So we have all these little negatives here, right? Which of the 2 ions in sodium nitrate then is going to migrate to neutralize those negatives? Na. So let's go ahead and take Na and draw that Na plus coming in to that cell. Remember, electrons leaving leaves this cell positive, so what ion from the bridge is going to neutralize that charge buildup? Our nitrate ion. Okay, so our cell is looking good. What I want to talk a little bit about, though, is what's physically happening. What do you see happening? Tell me about the colors. Let's start with the cobalt. What's happening to the cobalt color? The +2. Cobalt solid's not going to be colored. Well, it's a color, but I'm referring to the pink of the solution. What's happening as time passes to the solution? It's getting more pink because we're making more CO +2. What's happening to the blue? The blue is getting less because we've got copper 2 ions being used up to make copper solid. There are 2 ways this battery can die. What are the 2 things that could happen? Yeah, the salt bridge is kind of free-flowing. It never really runs out, okay? So that's okay. I didn't name you. No one knows who you are. Chuck. Kidding. It's okay, Chuck. It's anonymous. I'd rather you say the wrong thing than not say anything at all. So what other things could run up? Well, maybe not. Let me take that back. What runs out of what? Cobalt solid. So what can happen is this could shrink away. And that's what happens. Our anodes always shrink. This is the best thing I've ever done in my life. You ready? You ready? The buildup is huge. You know why they shrink? Because they're anode rexic. Ah! Isn't that the best thing ever? I came up with that one all by myself. Isn't that good? So the anodes are anode rexic. Those shrink away. What's happening to the cathode, though? It's getting bigger. This is where the solid deposits. So this gets bigger and bigger and bigger. And I've heard people say fat cat. It's getting fatter. But nothing even compares to anode rexic. You will never forget which one shrinks and which one gets bigger, ever, because of that. Because I'm a rock star. I'm just kidding. I'm just kidding. Okay. So last thing you need to do with these is to write something called shorthand notation. Shorthand notation is a quick sentence that describes what's going on in the cell. So how you do this, you always do the oxidation half reaction first, and then you do the reduction half reaction in this sentence. Once you see it, you'll remember where it's coming from. You've done this before. So go to the oxidation half reaction. This is in alphabetical order. You can go to the anode or go to the oxidation. A friend of mine used to say run to the OR. So we go to the oxidation side. Look at this. What's the first thing you see? Cobalt. No charge. Cobalt solid. Draw a single line. And then what happened to cobalt? It became cobalt plus 2. That is describing the first half cell. And then you draw a double line. Is this coming back to you guys? All right. And now you're going to go to the cathode. And what do you see? Cu plus 2, and then Cu. If I were an awesome teacher, I might take a piece of paper, and that'd be the only thing you have on it right there, and you have to recreate all this stuff. Which you can, because this is telling you what's oxidized. This is telling you what's reduced. That's all you need to recreate all of that. The last thing we didn't do on this, which it said they wanted us to do, was calculating the E. So let's review how to do that from yesterday. This one's easy because they already told us what's oxidized and reduced. So I'm going to write my half reaction CO going to CO plus 2 electrons, and then Cu plus 2 electrons going to Cu. I need to look at my voltages. I know the copper one. While I'm writing that down, you guys look up the cobalt one for me. This is 0.34 volts. I pulled it off the reduction potential table as it is because it is reduction. This is oxidation. I'm not going to see it as is. It's going to be backwards. What is that on the table? Did you change the sign? Okay, so it was negative 0.277, but because it's oxidation, we have to change it to positive 0.277. So we're going to add those puppies up, and we get an E of 0.617 volts. All right, and there is our E naught, not being standard conditions. If I were to ask you for the overall balanced equation, this one's easy because it's 2 electrons and 2 electrons, so that's already balanced as it is. Done. Okay? That's beautiful, Jasmine. She has like 87 colors on a Voltaic cell. Every electron's a different color. Okay, let's try a different one. This is going to be same concept. We're doing everything the same, but the setup's going to be a little bit different. So what's the deal? A cell is made from copper plus 2, iron plus 3, 1 molar solutions. How is this different than what we did before? There's a big difference between this and what we just did. What? Well, that's a difference. That's not what I'm going for, but there's something even more different than what we did before. Perfect. We don't know what's being reduced and oxidized. All this person's saying, hey, here's some junk, make a cell. Well, we want to make sure it's going to be a cell that works, so we need to figure out, in order to get a positive E, what needs to be reduced and what needs to be oxidized. So my suggestion in a case like this, since we have a reduction table, write both of these as reduction half reactions. Let's just do that first. How do I write that as a reduction half reaction? Good. And then we're going to write the other one, Fe plus 3 electrons makes Fe. So let's go ahead and look up those reduction potentials. Again, I know this one is 0.340 volts. And what is the other one? Negative 0.04 volts. All right. One of them has to say reduction. One of them has to become oxidation. Which one is more apt to be reduced and why? The copper is more apt to be reduced because it has a higher or a more positive reduction potential. It makes sense. Who wants to be reduced? The one with the bigger reduction potential. So we're going to leave that one alone and leave that as reduction. And this one we're going to make oxidation by changing that sign. So we get iron going to iron plus 3 electrons. Somebody calculate the, oh, never mind. Math is not that hard. I'll probably mess it up though. I'm just waiting on that to happen. All right, is that correct? Yes. All right. Now let's go ahead and add up our equations. Remember, we don't multiply the voltage by the coefficient because of the push per. Was it Jasmine I pushed down the stairs? That's what you need to go watch. I forgot. I pushed you down the stairs yesterday in my analogy. All right, so we're going to multiply through. I want you all to practice doing this in one step. The top is by 3 and the bottom's by 2. So 3 Cu plus 2 irons gives us 3 Cus plus 2 iron plus 3s. Okay, that is the hard part. That was what we needed to do to figure out what's oxidized and reduced. So now let's go ahead and start our drawing process. All right, what do you want on the left? Which element? You want to put copper here because it's first? We'll put copper plus 2 electrons makes copper. Okay, this is going to be a copper electrode in a 1 molar copper 2 solution. This is oxidation or reduction? Reduction. So what's the name of this electrode? Red cat. Or consonants and vowel game. This is the cathode. Oh, I forgot to label my electrodes. How do you know how to put a battery into something like your calculator? How do you know how to do it? Positive and negative. Those are arbitrary signs. Don't sit there and try to justify the charge because if you look at ion migration, it's contradictory. So what I need you to do is just think of it as a label like salt and pepper, peanut, butter, and jelly. Doesn't really matter. What it is to indicate universally something that is known. Cathode has a positive sign on it. Cats are positive because I have a cat. There's a T, a positive in the middle of cathode. Then someone said, this is a little much for me, cats are positive. Positive. Yes. Okay. That's an arbitrary label. You do need to know how to label this. We'll go back on the other one and label it in a second. Okay, and we're going to connect it to the anode, and the oxidation that's occurring is iron to iron plus 3. Oxidation occurs at the anode. We have our iron electrode in 1 molar iron plus 3 solution. Let's attach those electrodes with a loopy wire. We've got to label electron flow. What directions does electron flow? Alphabetically, anode to cathode. So in this case, we're going this way. Now, on the AP a couple years ago, this question asked direction of electron flow, and they required that the students showed it on the wire. If you did this, you didn't get the point because the professors were saying you guys thought it was going through the glass. Yeah, so I know it's ludicrous. But, I mean, to me, that meant they know which way it's going. No. Make it go through the wire. And even if you did this, they were like, oh, they think it's jumping. Yeah, so I'm not kidding. These professors are wackadoos. All right, so anywho, put it on the wire. Okay, charge buildup is going to be an issue, so we need to neutralize that by adding a salt bridge. Let's use a different group 1. Lithium nitrate. All right, lithium nitrate. Okay, electrons are going into the left beaker here, into the cathode. So the charge buildup there is negative. What ion is going to come out? Lithium. And then the nitrate is going to come out of here because the electrons are leaving. So what's left behind are a bunch of positive things. So naturally the nitrate will migrate there. That'll neutralize the charges, start the process again. Yes? Okay, think about the electron flow. Electrons are going into here. That's a negative charge buildup. So the lithium then wants to, the lithium's attracted there. Okay? Why this is confusing is, and that's what I was saying about the signs, you see how it's positive here? Why would a positive thing be attracted to a positive electrode? And that's the thing, it's not attracted to the electrode. It's just confusing. Don't try to rationalize the signs, that they're labels. Because as soon as we get to electrolytic, they're reversed. A way that I'm going to help you remember this is through the saying EPA Van. There's Vanna White. I originally used to say Vanna White works for the EPA and did it that way, but then someone came up with EPA Van. But we kept Vanna in the picture because it's Vanna. Y'all know who Vanna White is, right? Wheel of Fortune. She used to turn numbers. Like physically now she just touches. Yeah, I think her job, her arms are going to get all flabby now because she hasn't exercised. But what the EPA Van stands for, and right now just worry about the Van, voltaic anode is negative. And here we had the anode and we said it was negative. The cathode is positive. This means electrolytic positive anode. But we haven't done electrolytic cells yet. We're not doing those till Friday. So just worry about Van right now. You guys doing okay? All right, so I think the only thing left for this is shorthand notation. Can someone tell me where I'm going to start? Oxidation, so I'm going to have iron, and then I'm going to have iron plus 3, then I'm going to have a double, and then I'm going to have copper plus 2, then I'm going to have copper. Now, if your solutions are something other than 1 molar, you'll see parentheses, and they'll have like whatever molarity that is next to the ion. If there's nothing, you assume standard conditions on that. So what's going to shrink? The anode, because she's anorexic, and that is the iron. So the iron's going to shrink away. The copper's going to build up. What else? What's going to happen to Fe's color, Fe plus 3's color in solution? It's going to get darker because we're making more of it. What's going to happen to the copper color? It's going to get lighter. It's going to start to fade. Will it go away? I don't know. It depends how much other stuff it's reacting with. There might be, you know, eventually this whole thing will get all mucked up and brown and gross if we let it flow forever and ever. What about rechargeable batteries? Any ideas? Nope. Wait, what? So we have a battery, it's dead. I put it into a charger, plug it in the wall. What's it doing? It's reversing both those equations and forcing electrons back, rebuilding our anode, making our iron back again, and recreating some copper too. And it never makes as much as it originally. You know, rechargeable batteries never work as well once they're charged as they do the first time. It's just the way it goes. And this is a very crude representation of that, but that's kind of the concept behind rechargeable batteries. You're flipping those equations back, forcing it to happen. Okay, tomorrow we're going to look at free energy with this stuff and the Nernst equation. I just got a good question about where is the charge, like what's the deal with the battery. What's happening with the battery, since the electrons are flowing through here, the way we harness it is by utilizing this spot and having connections here. So a lot of times you'll see a voltmeter here, or you put, and I'm going to build this, I hope to get to it by Friday, show you how to run a radio off of chemicals. I actually plugged the radio in here, and I have one end of the radio connected here, the other connected there, and the charge just passes right through it. Potential difference.